So for today, this really last section of Unit 3, super easy one. It's just how to graph inequalities in two variables. Okay, so the solution to an inequality means the same thing as a solution to an equation. If it's a solution, it makes the inequality true. It satisfies the inequality. If it's not, it doesn't. So we could test these out. And we'll make this very quick. So if we're given some inequality in two variables, x's and y's, and we want to know whether each of these 3 points is a solution, just plug them in and see. Right? What would I get for the first case here? If I plug in 7 for x and 4 for y, I would get the statement 4 is greater than or equal to negative 2 times 7 plus 9. And that's either going to be true or false. If we simplify that on the right side, what do we get? Negative 5. Negative 14 plus 9 is negative 5. Is that true or false? True. So what's that mean? So yeah, it is a solution, isn't it? Right? If it's true, if the ordered pair satisfies the inequality, then it qualifies as a solution. And remember, this is an example where it's greater than or equal to, right? So if that had been 4 is greater than or equal to 5, for example, would that have been true? Is 4 greater than or equal to 4? Yeah, it is, right? Because it's equal to 4. Does that make sense? Okay. So if it's a greater than or equal, the numbers on the left and right could either be equal or they could be unequal but satisfy the inequality, right? Let's get earbuds away, please. I don't want to see any earbuds. And then if we get an example where they don't work, and let's see, I think that one won't work. Let's try it. 10, negative. Oh, actually, that will work. How about this one? Yeah, let's try this guy. If we try. If we try this one, we'd get 3 is greater than or equal to negative 2 times negative 1, right? Plus 9. That's not going to work, is it? I'm going to get 3 is greater than or equal to 2 plus 9. False, not a solution, right? Okay, give me thumbs. That all make sense? No big deal, right? Okay, so the main issue for the day then is how do we graph these things? And there's two methods that textbooks teach. Here's the method from our textbook. I don't really like this one as well, but it's fine. It works. What are the steps? Well, when we graph inequalities in two variables, there's always going to be two parts. There's going to be the boundary line and a shaded half plane. Give me 1 to 5 on that. Have you guys ever graphed this stuff before? Okay, maybe a little bit. Okay. So the first step is to ignore the inequalities and graph the boundary line first. With one thing you got to keep in mind, if the inequality sign does not include an equal sign, then the boundary line is not included in the solution. It's just the boundary only, but it's not part of the solution. And so we graph that as a dashed line, right? So that stuff goes together. If the inequality sign does include an equal sign, then the boundary line is part of the solution. And so we use a solid line for our boundary, right? So we're going to graph the boundary either dashed or solid. Then this is fine. You could just choose a test point that's obviously in one of the two half planes that is created by the boundary line. Think what that means. Now, if I've got an XY plane and I create some boundary line. So here's my boundary line. Let's say it's a solid boundary line. There's my boundary line. It goes forever, and so it's going to cut that infinite plane into two infinite half planes, right? We're just going to pick a point that's either above or below, or if it's a vertical boundary line, to the right or to the left of our boundary line, and plug it in and see if it works. If it works, if it proves to be a solution, then I shade the half plane that includes that solution, right? If it is not a solution, I shade the other one. Okay. That's one way to go. I kind of prefer this way, honestly. I prefer this method. Use either one. Maybe try them both at least once, so you're just familiar with them. If you put the inequality into slope-intercept form, which is often useful to do anyway, sometimes it's not, but when we look at some examples here, I'll tell you why putting it in slope-intercept form, well, when we see an example that applies, I'll tell you why that's probably a lot better way to go than trying to use that cover-up method that you guys learned from the videos. Remember that, where you just find the intercepts and you connect the intercepts with a line? Is that ringing a bell from the video you watched? Okay. That's okay sometimes. I mean, it's fine, but this is almost always a little bit easier. So put it in slope-intercept form, graph the boundary line just like we talked about, either solid or dashed, depending on the nature of the inequalities. And then if it's in slope-intercept form, you can always tell immediately whether you're going to shade above or below the line. If you end up with something like this, y is greater than or equal to something, then this is telling you that you are going to shade above the boundary line, right? Think why that is. You want to include all of the y values are greater than the boundary line. Doesn't greater than the boundary line mean above the boundary line mathematically, right? Because y is the axis. Okay, and then by the same thinking, if you how many times am I going to do that, you think? Probably a lot, huh? Add like y is less equal to some stuff. Just based on the direction of the inequality, okay? Makes it really quick. So let's try a couple of these real quick. How about this guy? So what's my first step? Boundary line, okay? Help me out. I need 2 points. Where do I start? Good. Okay, I'm starting at the y-intercept, which is -1. And what am I going to do? Up 2 over 3, okay? So we're going up 2 over 3. I'm creating another point. And what type of a boundary line am I graphing here? Dashed or solid? Dashed. Obviously it's dashed. How come it's dashed? Because of that. Because there's no equal sign on the inequality, it's dashed. It's not included in our solution. So there's our boundary line. And then which way are we going to shade? We don't even have to test a point if it's in slope-intercept form. Which way am I shading? Bottom, yeah. Okay, because of this, we're going to shade right? Make sense? Yes. Okay, if the boundary line is vertical, then we'll look at one like that. Yeah, we'll see one like that. Okay, how about this guy? So here's an example where, like, if we were to find the x-intercept and the y-intercept, why is that a bad idea here? Why am I going to maintain that just putting it in slope-intercept form is always going to be a better way to go? Like, what's wrong with this? If I cover up x to find the y-intercept, it's no big deal. I just get 4, don't I? Right? But if I cover up y to solve for the x-intercept, yikes, I get a fraction. Okay, that's likely to happen often. So we're really just better off picking a convenient point and using the slope from slope-intercept form. Usually the convenient point is going to be the y-intercept, but not always. So we'd put this in slope-intercept form. What would the steps be to put it in slope-intercept form? Okay, good. So 3y is less than or equal to negative 5x plus 12. Last step. Divide by 3. Good. Excuse me. So we end up with y is less than or equal to, let's split that fraction so we get negative 5/3 x plus 4. Give me thumbs on that. Does that all make sense? Okay. That's easy to graph, isn't it? Right? So where do I start? My starting point is 4. And I make a slope triangle that gets me a second point. Where do I go? Good. Down 5/3. I tell you what, we'll pick this up tomorrow, finish it up.